The plot of reaction velocity V versus substrate concentration S, based on the Michaelis-Menten equation, can be used to determine kinetic parameters, such as Km and Vmax. However, the V versus S plot suffers from one major disadvantage. It produces a nonlinear curve, which is less predictable and requires more data points to be accurately drawn graphically. The Lineweaver-Burk plot. To improve the graphical determination of Km and Vmax, Lineweaver and Burk rearranged the Michaelis-Menten equation as follows. By taking the reciprocal of both sides of the Michaelis-Menten equation, Lineweaver and Burk transformed it into the linear form y equals mx plus a. By comparing the obtained equation to y equals mx plus a, 1 over v corresponds to y and 1 over s corresponds to x. The y-intercept corresponds to 1 over Vmax, while the slope m is equal to Km over Vmax. The plot of 1 over v versus 1 over s, also known as the double reciprocal plot, produces a straight line as shown. The values of Km and Vmax can be determined from the slope m and the y-intercept of the plot, as indicated. Although this plot yields a straight line, it also possesses two main disadvantages. The first disadvantage is that the substrate concentration is expressed on the x-axis as 1 over s rather than s. In the Michaelis-Menten plot, substrate concentration is expressed as s, leading to a uniform distribution along the x-axis. For example, as shown in the table, varying the substrate concentration from 0.05 to 0.35 millimolar produces equal increments of 0.05 millimolar. In contrast, in the double reciprocal plot, where the x-axis represents 1 over s, the same substrate concentrations give rise to non-uniform spacing along the x-axis. The second disadvantage is that the data point at the lowest substrate concentration, typically the least accurate, has a disproportionate influence on the plot. For example, the data point at which S is 0.05 millimolar, or 1 over S is 20 times 10 to the power of 3, is the least accurate due to substrate depletion during the enzyme assay, yet it has the greatest influence on the plot. At present, with the availability of various curve-fitting programs, enzymologists have reverted to using the Michaelis-Menten equation and V versus S plots for the determination of Km and Vmax. Nevertheless, the Lineweaver-Burk plot continues to be used under certain circumstances. The final table summarizes several plots that have been derived over the years through rearrangement of the Michaelis-Menten equation. Although the resulting equations retain the format of y equals mx plus a, the parameters corresponding to the x and y-axis vary. In the Eddie-Hofft plot, for example, the y-axis is v, whereas the x-axis is v over s. The y-intercept is equal to Vmax over Km, and slope m is equal to minus Km. An equation analogous to the Lineweaver and Burk equation is the Scatchard plot. This plot is commonly used in binding studies to determine the dissociation constant of a ligand for its receptor. Here, F and B represent the free and bound ligand, respectively. Vmax represents the maximum amount of bound ligand, which is analogous to Vmax in enzyme kinetics. And Kd is the dissociation constant. The advantages and disadvantages of the different types of plots are summarized in the table as shown.